It's past midnight in interior Alaska. It is minus 45 degrees Celsius. Cold enough that if you threw a cup of boiling water into the air, it would freeze before it hit the ground. And through this frozen darkness, a 3,000-ton freight train is moving. Inside the cab, one man watches the track. He has been awake for 9 hours. His breath fogs the instant it leaves his mouth, and outside the windshield there is nothing. No towns, no headlights, no sign that the rest of the world still exists. Just 2 rails, a wall of black spruce, and the long white beam of a single headlight cutting into the night. Here is something strange. To slow this train down, the engineer does not push harder on anything. He does not add pressure. He releases it. He lets air escape. And at minus 45 degrees, that single fact, that you stop a train by letting go, not by pressing down, is the difference between arriving safely and a catastrophe you would never walk away from. So why does releasing air stop a 3,000-ton train? What happens to that air when it is this cold? How does a diesel engine even start when the fuel itself is close to freezing solid? And why, no matter how experienced the driver, is there almost always a second person sitting in that cab? Let's spend one night inside this machine, hour by hour, and find out. Before we climb into the cab, if you like the hidden engineering behind the machines that move our world, take a second and subscribe. It genuinely helps this channel keep going. Now, let's go back to the beginning of the night. Long before the train moves, the fight has already started. It is late afternoon, and the sun in interior Alaska in deep winter barely bothers to rise at all. The thermometer on the yard office reads minus 38, and it is still dropping. Here's something almost nobody thinks about. That massive diesel locomotive sitting in the yard has not been switched off. In fact, it may not have been switched off for weeks. Down south, you turn a truck off when you park it. Up here, at these temperatures, shutting a diesel engine down is one of the most dangerous things you can do to it. Diesel fuel does not freeze all at once, like water. As it gets colder, wax crystals begin to form inside it. The fuel goes cloudy, then thick. Then it turns to a gel that will not flow through a fuel line at all. Engine coolant can freeze and crack the block. Oil turns to the consistency of cold honey. So the engines are left idling around the clock, a low, endless rumble in the dark, burning fuel just to stay alive. Think about that for a moment. A large freight locomotive can burn on the order of 15 to 20 liters of diesel an hour, just sitting still, doing nothing, going nowhere. Over a hard winter, a railroad can burn a small lake of fuel, simply keeping its engines from dying. It sounds wasteful, and it would be anywhere else. But the alternative is worse. Restart a cold-soaked diesel that has been sitting at minus 45, and you risk cracking a cylinder, snapping a component that has gone brittle, or simply failing to start at all because the starting batteries themselves have lost most of their punch in the cold. A battery that gives you 100% of its power at room temperature can drop to barely half of it at these temperatures. So the golden rule of the far north is simple, and it is the exact opposite of what you were taught about saving fuel. You keep it running. The engineer walks the length of the locomotive with a flashlight, and this walk-around is not a formality. He is looking for the enemy's first moves. Frost building where it shouldn't. Airlines stiffening. A hose that has gone hard and brittle. He checks the fuel. Is it the special winter blend? Cut with additives and sometimes blended toward a lighter grade, so those wax crystals can't lock it up. He taps a gauge that has gone sluggish. He listens to the engine. After enough winters, an engineer can hear a problem before an instrument ever shows it. A change in the idle, a note that is slightly wrong, the mechanical equivalent of a cough before a fever. He also checks something most people never picture: the sanders. Buried on the locomotive are boxes of dry sand, and pipes that can blow that sand directly onto the rail in front of the driving wheels. On steel that is glazed with frost or packed snow, the wheels can spin uselessly, or worse, slide. That sand is what gives 3,000 tons something to grip. At minus 45, even the sand has to be kept dry and flowing. because damp sand freezes into a useless lump. Every single system, right down to a box of sand, has a cold weather way to fail. And already, before a single kilometer, you can see the shape of the whole night. Up here, the cold does not attack the man first. It attacks the machine. The train pulls out into full darkness. Behind the locomotive stretch dozens of freight cars. 3,000 tons of steel and cargo, rolling on nothing more than a thin film of contact between steel wheels and steel rail, each contact patch no bigger than a coin. Now, back to that strange fact from the beginning. To understand this train, you have to understand its brakes, because they work backwards from what your instinct tells you. You would think that to stop a train, you increase pressure in the brake line, push harder, brake harder. But it is the opposite. On a train, the brakes are held off by air pressure. A pump fills the entire brake line, car to car to car, with compressed air, and that pressure is what keeps the brake shoes pulled back and away from the wheels. To brake, the engineer releases air. The pressure drops, and springs and pistons slam the shoes onto the wheels all down the length of the train. Why on earth build it that way? Because it is a fail-safe. Imagine the alternative. If brakes needed air pressure to come on, then the moment a hose burst, or two cars broke apart in the middle of nowhere, you would have a runaway train with no brakes at all. Instead, the system is built so that losing air means stopping. If a coupling snaps at -45 and the line tears open, air escapes and the train brakes itself automatically before anyone in the cab even knows what happened. The system does not trust the driver to react in time. It trusts physics. Lose pressure, and it stops every time. And this is where the cold gets its hands into everything. That brake line is full of ordinary air, and ordinary air carries moisture. Every time the compressor squeezes air, it wrings a little water vapor out of it. And at -45, any trace of that water wants to freeze. A tiny plug of ice in a brake line can stop air from moving where it needs to go. Now think about what that means on a train that can be well over a kilometer long. The signal to brake travels down the line as a change in air pressure, car to car to car, and it takes time to reach the very last wagon. One frozen fitting somewhere in that chain, and part of your train is trying to stop while another part is still rolling free. So the train carries air dryers and additives to pull every drop of moisture out of the system, because a frozen brake line is not a delay. It is a train that cannot properly control its own stopping. There is a second, quieter piece of genius here, and it is another thing that runs backwards from instinct. On long downhill grades, the engineer often barely touches the air brakes at all. Instead, he uses something called dynamic braking. The same electric traction motors that drive the wheels are flipped into reverse. They become generators. The moving train tries to spin them, they resist, and that resistance drags on the wheels and slows the train. The energy of 3,000 descending tons is turned into electricity and dumped as heat through banks of grids on the roof of the locomotive. Why bother when you have air brakes? Because riding the air brakes for kilometers downhill overheats the shoes and wears them out. And in this cold, it also risks the very freezing and ice problems we just described. So the machine slows itself, for long stretches, by running its own motors in reverse. No shoes touching wheels at all. 3 hours in, and the temperature outside has slid past -42. This is where a new problem appears, one you can't hear and can barely see. The track itself is changing shape. Metal contracts when it gets cold. That is not a small, abstract fact out here. It is a physical force running for hundreds of kilometers. Modern rail is welded into enormous continuous ribbons of steel, and when that steel drops to -45, it shrinks. It pulls against itself with tremendous tension. In the worst cases, a rail can crack clean through, a pull apart. Railroaders call it, leaving a gap in the track wide enough to drop a coin into, sitting in the dark, directly in the path of 3,000 tons. So the engineer's speed is not really his to choose. It is dictated by the cold. He runs slower than he would in summer, reading the rail ahead in the headlight. Because at these temperatures, brittle steel behaves differently. Warm steel bends a little before it fails and gives you warning. Cold steel can simply snap. The rail he is trusting his entire train to has, tonight, less margin than it has on any summer day. There is a strange symmetry to this that railroaders know well. In the blazing heat of summer, the opposite happens. The same welded rail expands, pushes against itself, and can buckle sideways into an S-shaped kink that will derail a train just as surely. Engineers call those sun kinks. So the rail lives its whole life caught between two enemies, expanding until it warps in July, shrinking until it cracks in January. The steel is laid and tensioned to survive both, but there is no temperature at which it is truly comfortable. Tonight, the danger is the crack, and the only defense is a slower train and a pair of eyes reading the rail in the headlight beam. And notice the pattern building. The cold attacks the fuel. It attacks the brake lines. Now it attacks the very ground the train runs on. This isn't about a man being uncomfortable in the cold. It is about 100 small systems, each with its own breaking point, all being pushed toward that point at the same time. No single one of them is dramatic. Together, they are the reason this job takes skill and nerve, instead of just a steady hand on a throttle. Here is the deepest part of the night, and the deepest truth about this job. At minus 45 degrees, you would assume the enemy is the cold biting at human skin. Bare skin does freeze fast out here. Frostbite in a couple of minutes on any exposed flesh. But that is not the real enemy. The engineer is inside a heated cab. He has layers, a thermos, a plan. The real enemy is failure you cannot see until it is too late. It is the pinhole of ice quietly forming in an airline. It is the seal that has gone brittle and is about to let go. It is the fuel that is 1 degree away from gelling in a line you can't reach. None of these announce themselves. There is no alarm, no dramatic warning. A summer breakdown is an annoyance. You stop, you wait, someone comes. Breakdown here, in this dark, with no road for 100 kilometers, and a heated cab that only stays heated while the engine runs, is something else entirely. If that idling engine ever quits, the clock that starts is not measured in hours of comfort. It is measured in how long a human body can last while the temperature inside slowly falls to match the minus 45 outside. That is why the train does not gamble. It carries redundancy everywhere, often more than one locomotive, so that if one dies, another can still move the train and keep the heat and the air alive. Backup air compressors, emergency supplies. The whole philosophy of the machine at these temperatures is not speed. It is never end up stranded, because out here stranded is the one problem that kills. And this is why the engineer's attention never really rests, even when the track ahead is straight and empty for kilometers. He is not watching for the obvious. He is listening for the almost nothing, a gauge that reads a hair low, a note in the engine that wasn't there an hour ago, the way the train responds a fraction slower than it should when he asks for a little break. On a summer day, he might file those tiny signals away and check them at the next stop. Tonight, each one is a question with only one safe answer. Deal with it now, while the machine is still running, still warm, still able to help you fix it. The moment it stops helping you is the moment everything gets harder and colder, very fast. It is 4 in the morning. This is the hour when the body most wants to quit. When your temperature naturally bottoms out and your eyes get heavy no matter how tough you are. And this is exactly why there is a second person in the cab. There is almost always a second crew member up front. Not for muscle, for attention. Here is the cruel thing about exhaustion. A tired man makes mistakes in silence. He doesn't notice himself failing. He misses a signal and doesn't register that he missed it. He stares at the track and stops truly seeing it. Fatigue doesn't feel like danger from the inside. It feels like everything is fine. So two people watch each other. They call signals out loud to one another. One sees what the other's tired eyes slid past. At minus 45, on brittle rail behind 3,000 tons that need 2 kilometers to stop, a missed signal is not a mistake you correct on the next try. It can be the last mistake anyone makes. Redundancy in the machine keeps the train alive. Redundancy in the crew keeps the people alive. Out here, a second set of eyes isn't a luxury or a regulation someone dreamed up. It is survival. The machine helps too, in its own unsentimental way. Locomotives carry what is often called an alerter, a system that quietly watches for signs the driver is still there and still responsive. If too much time passes with no input, no touch of a control, it beeps. If the beep is ignored, it escalates. And if it is still ignored, the machine assumes the worst and brings the train to a stop on its own. It is another failsafe built on the same grim honesty as the brakes. Do not assume the human will stay awake. Assume he might not, and make the train survive that too. But a machine can only catch a person who has already gone under. The second human catches you long before that, in the quiet minute where you are just starting to fade and haven't noticed yet. And there is a quiet dignity in it that the passengers of the world never see. Two people in a warm box of light, sliding through the coldest dark on earth, keeping each other awake, so that everything the rest of us take for granted keeps arriving on time. No audience, no applause. Just a job that has to be done right, because the cold is always keeping score. Somewhere in the last hours before dawn, something almost always goes slightly wrong. Not a disaster, a symptom. Maybe the brake pipe pressure at the rear of the train is reading a fraction low, which could mean nothing. Or could mean air is leaking somewhere out in the dark. Maybe the train is taking a heartbeat longer to respond than it did at midnight. This is the moment the whole night has really been preparing for. Because here is the thing about this job that nobody outside it understands. The skill is not in handling the emergency. The skill is in catching the problem while it is still boring. A good engineer spends his entire shift making sure the dramatic moment never arrives. He slows down before he needs to. He tests the brakes early, on a stretch where a poor response costs him nothing. He treats a gauge that is one notch off as a message, not a nuisance. Out here, the difference between a routine night and a rescue operation on the news is almost never a single heroic decision. It is 100 small, unglamorous ones, made correctly in a row, by someone who refused to assume everything was fine. So he backs off the throttle, he watches the pressures settle, he runs a little slower still. Whatever the cold was reaching for tonight, it doesn't get it, not because nothing went wrong, but because someone saw it coming. Slowly, the sky does not so much brighten as turn a fractionally lighter shade of black. The train is nearing its destination. 12 hours ago, it was a set of cold machines fighting to stay alive. Now it has carried its 3,000 tons across a stretch of the planet where almost nobody lives, where the roads give out, where the only reliable way to move heavy freight through the deep winter is exactly this: a chain of steel, an idling engine that was never allowed to sleep, and two people who stayed awake to watch it. To bring it in, the engineer does that backwards thing one last time. He eases off. He releases air, gently, feeding the brakes on down the length of the train, letting 3,000 tons settle toward a stop measured not in meters but in kilometers. He does not fight the train. He talks it down, and then the engine keeps running, because it always keeps running. Up here, you do not switch it off. The frost does not care whether you are tired. The engine does not care whether it is Christmas. The rail does not care that you have done this 100 times before. Out here, the machines and the people who run them share one single job: keep going, no matter what the temperature says. Everything about this night, the engine that never stops, the brakes that work by letting go, the second pair of eyes in the dark, exists for one reason: not comfort, not speed, survival. The quiet, unglamorous survival of a system built to refuse to fail. Most of us will never see any of this. We will never stand on that platform at -45, or hear an engine idling through a night that long. But almost every product on the shelves of a northern town at some point moved through a night exactly like this one, carried by a machine that was not allowed to sleep, and a person who was not allowed to either. If you made it this far, hit like. It tells me you want more of these hidden engineering stories. And tell me in the comments, could you do it? One night, at -45, 3,000 tons, and no road home? I read every reply.